Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. I'm Rita, and I'll be hosting this webinar. It is our pleasure to have Promecon with us today, who will be presenting this webinar titled Electric Arc Furnaces, More Taps, Less Energy. Now, I'll provide some housekeeping information before we start. First of all, please send your questions throughout the webinar, and we will allocate some time at the end to address any questions or concerns that you may have. If your question doesn't get answered today, it will be available to be answered at a later stage. For any related content on the webinar, please click on the widget shown on your screen. And if you have any tech issues, please click on the help icon. And now please allow me to welcome Hans Conrad, who will begin the webinar.
Well, thank you very much for the introduction, and thanks for joining this webinar today. I will be speaking about our measurement of gas flow as well as gas composition for electric arc furnaces. More taps, less energy. So maybe I start off with a brief introduction of our company. The company Promecon has been around for nearly 30 years now, and we have always been specialized in measuring hot process gas in heavy industry processes. So since we started, we have been actually measuring or focusing on measurement in cement plants, power stations, or waste to energy plants, as well as in the smelter business for steel as well as for non-ferrous products. So whenever you have a combustion process or a thermal smelter process with hot and dusty gas, that's really where Promecon comes into play. This is our specialty. We do not measure any clean media or any emissions on stacks. We are fully focused on the process itself, where the gases are hot and very, very difficult to measure. And we do this in order to help producers of metals or producers of energy or of cement or lime to optimize their process in order to reduce energy waste, increase product quality, enhance process stability. So all the things that you are usually battling with and fighting with, and that you are struggling to find the reason for, any process instability, that's where we really come into play. And the field of hot gas measurement is, I would say, widely neglected, especially in the heavy industries. And the reason for that is that it's so hard to do. So I think today I have some very interesting topics, especially in this case for electric arc furnace outlet, to measure outlet furnace gas. So let's dive into this. The industries that we have so far served in the world are power generation, here mainly solid fuels, such as coal, but also biomass, and then waste to energy, which is also quite difficult process, steel plants, and in steel plants, not only EAF, but we also have been doing BOF, sintering, dedusting, pelletizing plants, you name it, or AODs, so various processes that have hot gas flows. Cement making is a leg that's very strong in our company. And then limestone, lead and zinc and copper as non-ferrous, as well as projects in the glass industry. For our main three markets, power, steel and cement, here's a selection of the projects that we've been doing worldwide. So we have been quite strong in many countries. Of course, from Germany, not far away from Berlin, Magdeburg, but also in the United States, we have been doing lots of projects, Asia, South America, South Africa. So we have developed our instrumentation by our own technology. So we have invented technologies which is you can't do this with conventional measurement methods and just make the instrument a bit better. You are relying on really inventing new methods and new ways of measuring these gas flows at temperatures up to 2000 degrees Celsius. Few new technologies, such as the correlation-based gas flow velocity, microwave-based pneumatic solids transport, as well as stack emission. Excuse me for a second. Today, I'm going to talk about infrared off-gas flame analysis, gas flow, as well as temperature and composition measurement. Excuse me. I will talk about the application of EAF, the measurement technologies that we are deploying. I will explain in a deeper way the infrared emission technology. I will also explain how we measure flow, which is not so easy when you have a hot gas at very high dust levels. Then I will show you a system overview. How is our system set up? How it is installed? And for that, I will show you some example of implementation. If you are from the steel industry, if you are having an electric arc furnace, at the end of this presentation, you will have a very good grasp of what we are doing and how we are measuring on your furnace. First of all, a very basic start. Our systems have been installed inside the process, on the ID fans, on the primary and secondary dedusting. Some even have installed our systems in stack, even though emission monitoring is not our main business, but various locations. Today, I would focus on the hottest location that you have, the off-gas duct right out of your furnace with very high process temperatures. I think due to this high temperatures, there are not many choices that you have when you want to measure the gas composition as well as the gas flow from your furnace. And I will explain these difficulties and how we have managed to resolve them. Where's the measurement point? The measurement point usually is directly behind the post-combustion gap. So as the hot gas comes out of the elbow, there's a small post-combustion gap, and our measurement sits right behind that. So we're looking onto the furnace gas before it can. So before post-combustion is happening, we are already measuring this gas, and therefore we are able to measure not only the furnace but also the CO, and you have a good idea of what's happening in your combustion. A little bit on the conditions that we find. Gas temperatures on an electric arc furnace when the power is on are fairly high. We're talking about 1800 degrees Celsius, 1400 degrees Celsius. Sometimes it can even peak higher. So it is very hard to have anything in there that is able to survive. Everything that you stick into this process needs to be cooled, so the heat load is taken off the material and the material doesn't start to decompose. The other thing that you can see here, dust concentration up to 50 grams per cubic meter. And anyone who has an electric arc furnace and looks into this post-combustion gap will see that you will have flames shooting out, but sometimes they are completely covered with dust. So the dust is a component that is also has to be managed during the measurement. A little bit on the history of measuring off gas from a furnace. There are several methods that have been deployed throughout the years in order to be able to get an idea of how the furnace is performing and what kind of off gas is coming off the furnace outlet. The first method, of course, is very classical. You have an extractive sampling method. So you have basically a lens that is water cooled, which you put into the duct. And this lens is then extracting part of the gas. And the gas is cooled down to a certain temperature where it can enter an analyzer. And this analyzer, it can be electrochemical, it can be a spectrometer, whatever, This analyzer is then measuring the constituents of the gas. Good idea. First principles. Now, the negatives are here again to be found in the process. You have a very hot process. That means you have to cool down the gas quite a lot. You run the risk of passing dew points. You can pass the water dew point, the acid dew point. So depending on the composition of the gas, the cooling process is difficult. With the gas itself, you also suck out all the dust. So you have a very contaminated gas that you put into your analyzer. And this contamination is a problem because you need to filter the gas and the filters will be clogging up with the dust. So any extractive gas measurement will come with a very high amount of maintenance and keeping the measurement going. That you have a time delay of 1.5 minutes because before it reaches the analyzer, need instrumentation value that, for example, the operator used to make any stop the electrodes. Also, on top of that, you don't have any flow measurement. It will only give you composition of the gas. You will have no idea of how fast, and therefore you will not be able to do any balancing of how much furnace, how much water has come out of the furnace. This will be impossible with the lens. So quite some draw with the classical method. Many people who have been used to maintain the engineers stuff in the world market measure the gas here putting into the duct. You have because you have a laser that's through the gas. You need to have a dye. So the alignment and as well as the gap that you critical when measuring. So alignment problems are another. The advantage that this technique out, of course, was measurement. However, you don't have a velocity here. So the third generation that came to market was that is capable of the gas as well, purely looking from the outside. So the system non-intrusive protrude into the duct, right? So by that, the for maintenance and for keeping the system running are much lower than with any other system. You have a system that's completely mounted from outside and has no contact with the process in an active way. So we're not exciting the molecules by a laser, but we're just having a detector that's measuring the infrared radiation of the gas. That's all. And by this, we are able to measure CO, CO2, water, but also gas velocity as well as gas temperature. So in the next slides, I'm going to explain of how this technology works so you have a better view. Let's first summarize quickly what has been on the market so far. You have an extractive measurement, long time delay, high maintenance, and no velocity measurement. Then you have a laser measurement, no extraction and real-time measurement, but still no velocity measurement, and also alignment issues because you need to come in from both ends. And then the McON IR system from Promecon, which is completely non-intrusive and non-extractive, real-time, and additionally, you are also getting a gas velocity measurement. Okay, how does it work? What we are detecting is infrared light from molecules, from gas molecules, basically from bipolar gas molecules. And that means that the molecules themselves irradiate a very high wavelength light, which means that not only it's detectable by a diode that can measure, let's say, up to 10 micrometers of wavelength, but on top of it, since the wavelength is so long and the energy levels to produce this light are so small, we can use the natural thermal radiation of the gas in order to detect this light, right? So as long as you have a gas that is at a certain minimum temperature of, say, 400 degrees Celsius and higher, 500 degrees Celsius, we can detect a spectrum of different wavelengths which stem from different molecules. You have a certain wavelength for CO, you have a certain wavelength for CO2, you have a certain wavelength for NOx or for H2O. So you can now detect how much of these molecules are present. So you can basically measure the concentration of these molecules in the gas. On the right-hand side, you can see a typical spectrum, and these spectrums are quite complex. There are quite a lot of wavelengths where you can look and see how much of that specific molecule is present. It's not so easy because these molecules overlap. They also change their width of their spectrum with temperature. So with higher temperature, the spectrum changes, which again is a good way to measure the temperature itself. And the biggest trouble here, all these molecules are covered with dust. So there's a lot of dust going through the duct. And as you know, dust is a solid body, and dust has its own spectrum, which is basically a black body radiation spectrum, or let's say gray body because it's dust, but it is a very wide range spectrum that covers all of the elements. So you need to measure at quite a few frequencies and do quite a lot of calibration and calculations in order to come up with a clean value for each molecule, which is basically the technology that we have developed for this measurement system. But the gas composition is not all. We also want to measure the gas velocity. Measuring gas velocity usually is quite simple. You have some obstruction in your duct. It could be a venturi or an airfoil or some other thing, or just a perforated plate or an orifice. And then you measure the delta P across that, and with the Bernoulli equation, you can then calculate the flow. With very high dusty and high temperature gases, this is very difficult. And the reason is high temperature gases do not give you much delta pressure because they are so thin. They have a very low concentration. A gas at 2000 degrees Celsius is very, very thin. It has a very, very low mass. And on top of that, you have all this dust coming along. So all impulse lines that you want to put to the process in order to measure the pressure will clog up with dust. You will have erratic readings. It's very, very difficult to do that. Promecon have developed a digital measurement way, and this digital measurement enables us to measure the time of flight of the gas directly. How do we do that? The most important thing is that the gas has a certain viscosity. So the gas flow pattern high concentration or higher temperature or lower temperature of certain molecules will not. So let's say the gas at one location has a typical time signature, as we call it, and it's giving you a certain, let's say, intensity. Then let's say 1 foot down or 300 millimeters downstream, the pattern of this gas radiation will not change over time. We call this a time signature or a fingerprint, yeah, over time. And if you have a sensor upstream and downstream, 300 millimeters offset, excuse me, you will have a very similar time signature, but you will see the time signature is shifted. It has a slight time shift. So you can measure these signals and you can digitize them. And this is why we call it digital measurement. The digitized signals go into a cross-correlation filter. And the cross-correlation filter will shift the signals and measure the statistical overlap. This is what we call a cross-correlation function. And if you have a certain overlap of a certain percentage, that tells you how much match these both curves have. So if you keep shifting them, you will find a maximum of overlap. And this maximum is the time of flight between sensor 1 and sensor 2. So what we are measuring basically is nothing but a digital time of flight. That's all, right? So you get, for example, 52.1 milliseconds. This is the time of flight of sensor 1 to sensor 2. And if you now know the distance of the two sensors, you divide the distance by the time. And what you get is meters per second or feet per minute or whatever. You get distance over time. It's a direct measurement of the velocity. There are several very big advantages to this measurement, and that's why we have sold it to thousands of applications in process gas flow. The measurement is completely independent of gas density. You can measure hot gas up to very high temperatures. This measurement is also completely independent of sound velocity in gas. You know, this is not like an ultrasonic measurement. This is completely different. We can measure from very low velocities up to transonic velocities with this. And of course, this measurement is completely insensitive to dust contamination. If we have high dust levels, we don't care. As long as we see this flow pattern and it repeats on the second sensor, we can clock it out and just say that's the velocity of a gas. Now, by measuring the temperature, which I explained before, and measuring the velocity and knowing the cross-section, we can get the standardized the temperature and pressure corrected flow. So we can tell you how much gas is coming out of your furnace. We can measure the gas flow rate out of your furnace directly. And since this measurement is digital, you will never have to worry about recalibration, about drift. This measurement will not drift over its entire lifetime, right? This is really the difference between a long play record and a digital recording. There will be no flaw and no drift and no influence on this. So you would always have a completely accurate measurement from day one to the very last day of this measurement. Very high advantage, and that's the reason why thousands of applications in hot process gas are using this measurement. So how does a system of Promecon look like? How does a complete system designed? We start at the process end. At the process end, you have what we call a water box. This water box is basically just an adapter that allows you to put in our sensors and look inside of the process. Now, since our measurement is installed usually on water-cooled ducts, we are looking through the water wall into the process, and our water box or our adapter needs to be water-cooled. You can see this labeled number 14, coolant connection. So you can directly connect this water box to your cooling water cycle of the steel plant. Then you can see the adapters coming out where our sensors are mounted. You can see, in this case, 4 sensors, 2 of them velocity sensors and the other 2 for constituents of the gas and temperature. You can see that these sensors have cables, which are black, but they also have yellow coolant connections, which are basically nitrogen, cooling nitrogen, that is put into the sensor head. And it's cooling the sensor. With the diodes need to be cool enough in order to see enough infrared light. If you switch off the cooling, the sensors don't measure anymore. But if you switch it back on, they start measuring again. So losing the cooling on the sensor will not destroy the sensor, but it will simply be a loss in signal. Then the coolant goes through the sleeve of the sensor into the process. So there's a small opening at the front of the sensor where the coolant medium can go into the process gas. And since that hole is very small, the sensor will always be on a slightly positive pressure. So we have a sealed pressure of the sensor towards the process, and that helps to keep the sensor clean, to keep all the optics clean, and have the sensor maintenance-free over a long period of time. And then we also have a small hose connected directly to the adapter. This is for purging the adapter from time to time and keeping the opening of the sleeve free, so there's no slag or dust collecting in front of our optics, because it needs to be clean in order to look into the process. So this is the front end. In the middle, there's more parts, much more parts. In the middle, there is what we call the field box. The field box contains basically the routing of the signal. So it routes the signal of the individual sensors to the main cabinet, which we will see later. But the other thing is that the field box has a nitrogen intake, and the nitrogen will then be distributed to all the individual sensors by a mimic of magnetic valves, as well as flow and pressure sensors, which supervise the flow as well as the pressure of the nitrogen to the sensor. So if someone switches off the nitrogen, there will be an alarm that the nitrogen has been switched off. If the nitrogen, however, is there and you have a nominal pressure, but the flow is too low to one sensor, then this is an indication that there might be an obstruction in front of the sensor. So in this case, there will also be an alarm that you would have to clean one sensor sleeve in order to make sure we can look into the process again. This is a very important part of keeping enough supervision on the sensors and understanding that they are mechanically working correctly. Next is the main cabinet, which can be seen here. The main cabinet is located somewhere in a switch room. It can be up to 100 meters away from the measurement. The field box in the middle should be fairly close to the sensors, because we would like to have a good cleaning impulse if we're cleaning the sensors. So these valves, these magnetic valves on the field box, should be close to the sensors. But the main cabinet, which is labeled 1, the central unit, this can be further away and can be located somewhere in a switch room or control room. This cabinet holds the HMI with all the screens where you can see the values displayed, you can display trends, and you can also reprogram parameters if necessary. But usually it's not necessary to perform anything on this cabinet. All of these values, the CO, CO2 and whatnot, of course, will be transmitted to your level 1 or level 2 systems. So you don't really have to be at the cabinet. And also via our protocols, you can transmit all the alarms and any other information that's necessary. Inside of this central unit, you have the individual component link boxes, you have the main control electronics, And of course, you have the routing of the signals as well as the power supplies coming in. So it's basically an industrial panel that you have in your plant on many locations. Outside of our battery limits, of our scope of supply, of course, are all the connections into your level 1 and level 2 systems. So this is all plant from the plant side. And that's basically the complete system if you install it on one of your EAFs. Needless to say, our system is modular. You don't need to have all the components, all of the sensors all the time. We have clients sometimes that say, I only want to measure CO and CO2. I don't want to measure velocity. Missing. So the system is smaller and it has less capability. But later on, if you would like to retrofit more parameters, it's no problem to do so. You can then retrofit the velocity later. Now let's have a look at some of the applications in Oman. It's a furnace of Danieli, the Italian company Danieli. They offer this measurement for their electric arc furnaces, and Danieli also offers, of course, control system in order to use this measurement for optimizing your furnace. So smart furnace controls, off-gas optimization can be done with this. Danieli uses that in their own system, Evo. There are other suppliers on the market as well who do that. There are companies like AMI or other people, Concept, that have also some smart systems to offer that. You can see the systems are installed on the side of this off-gas duct. You can look here on the off-gas duct side view. You have the 4 sensors installed. Actually, if you have a look at this blue arrow, this is where the sensors are installed. There is a fire protective cloth over the sensors to cover it from direct heat that sometimes happens when you're recharging with a bucket. You have some parts that are quite hot. Also, when you pull the electrodes, you can have quite a lot of radiation heat. So the direct protection of the sensors is by this cloth. It's very important to protect the sensors if they are that close to the furnace. But obviously, this happens. This can be managed quite well, and there's quite a good protection here. Another example of an installation is here at a furnace from SMS. This is a furnace in a plant in Germany, in Riesa. The sensors here are located from the side, again, to look inside the duct. Here you can see another advantage of our system. Our system can be tilted. So these sensors do not look straight into the duct on a horizontal plane, but they are looking upward. The reason for that is that we would like to see right into the hot gas and not due to this post-combustion gap look through the cold gas. Now you might question why are the sensors in the middle of the duct? Why they are mounted on the lower end? Well, in this case, very simple. You can't see this on this drawing. They are mounted on the lower end because you have a lot of ducts and piping that is in the way. You know, it's not so easy to find a good location or a good spot where you can put the sensors onto the duct. So sometimes you have to move them further up, further down, and then they don't look into the center of the duct anymore. So for that reason, you can tilt them. Another very big advantage, since we do not have to protrude into the duct, and we also don't have to mount our technology from both sides, but only from one side, and that's enough. So add some values here. Our measurement system gives out real-time values, 2 heats that you can see. And you can see on this the online reading of CO2 in blue, the online reading of CO in yellow. You can also see velocity in gray. So this is the total gas flow from the electric arc furnace coming into the EAF. Of course, this looks different if you are installing our system onto a con steel. Of course, you have a continuous charge. And in this, you don't see these. So this is where you can see, and it's very, you can see the CO coming, these events. So if you're lancing, you will see changes in the off gas. If the operator has to, over blowing oxygen, do I want to increase my yield of scrap, use of natural gas, etc., etc. So these decisions can be supported by not only listening to the sound of the furnace or having your time sequence, but really also having this off-gas information that gives you an additional angle, an additional perspective to judge about how your furnace is currently working and in which phase it is, and how you can shorten maybe the power on time or reduce your gas flow to the furnace. Here, a very nice example, increase oxygen. The oxygen is shown here as well. Please note, our system does not measure oxygen directly because we measure molecules, bipolar molecules. Oxygen O2 is symmetrical and it also has radiation, but much, much smaller wavelengths. So it doesn't shine necessarily because the temperatures for that needed to be much, much higher. But we have an oxygen value here from the oxygen lens. And you can certainly see that when oxygen is blown, for example, here, you have a reaction in CO, and you have a reaction in CO2. So you can also see what lancing the oxygen does to your process. Example here, in this case, we will also show you off. This shows you also, of course, that when many process steps, they are running in parallel. So sometimes they're running in parallel, sometimes they are offset. If you mount a little bit away from the furnace outlets, a little bit further, they have application, for example, in an AOD, where we are measuring very far away from the lancing point. It's about 40 or 50 meters up. And in that location, there is simply no CO to be found. It's just CO2. It'd also be interesting if CO may be inlet point, or also a little bit down, and how much of that goes into low energy consumption of this probe. Our measurement, because of course clients want to know how measurement of Promecon correlated with a classical extractive measurement. Is that comparable? And in this case, you can see very nicely that they are trending exactly on top of each other. You have in orange or in amber the Promecon measurement system, and below you have the extractive measurement system. Those two measurements have been aligned for time. Yeah, what do I mean by this? Alignment for time means that our measurement is delayed by 2 minutes for comparison. Yeah, and the reason for that is that the extractive measurement needs 2 minutes to show a value. So if you go down in CO2, it takes 2 minutes on the extractive measurement, or sometimes 90 seconds, before it also starts to fall down. So you lose 1.5 minutes before you know what's happening. But if you put them on top of each other, you will see that our measurement always anticipates what the extractive measurement will be doing later. In order to really match them, you have to align for time, the time advantage of the Promecon measurement. You have these gaps in the data. The problem with that is for the extractive measurement, you have to blow out the lens, especially in electric arc furnaces. You can have quite high dust levels. So dog up with extracted dust and your hands free, and to keep the filters free. So whenever you do that, there is a gap in the data. And of course, the operator in this case cannot see what's happening. The Promecon data at the top, of course, doesn't show this. Our data keeps on going all the time, and we don't have any gaps in between. Basically showing the direct comparison of the two measurements. Now, we have come to market with this measurement only a few years ago. Promecon has been around for about 30 years. We have been starting our journey in 1990, but it was on cold gases. Cold is everything that's colder than 600 degrees Celsius. Anything that's below 600 tactile measurements, electrostatics. You have the gas flow. You can, for example, a K-type thermometer. The hot gas are difficult. Something that we came to market years ago. A very systems. Of the systems that we so far, you can also see Fs. Some of them are also Châtelet installed. We think D is a very interesting application. And you can see all the applications that we can do side off gas, from AODs, OFs, even VODs. We have done those, but those are certainly possible. And then, of course, we can also look in which we're doing, and the string of burners. So this is, let's say, the full range of applications for this infrared measurement. Okay. What I've shown you today is a unique measurement for. Oh, okay. And the flow measurement is pretty much calibration and drift free. It does not need to be readjusted, or we don't need to have any adjustment on the on drift, because it's drift free, absolutely drift free. And the same in principle applies also for the measurement of the constituents, right? So you have a direct gas flow measurement as well as a measurement of the gas composition. So you are not only able to optimize the control of your furnace, but you're also able to optimize the complete mass energy balance, because you can also measure the gas velocity and the total gas flow out of your furnace, not only the gas composition. And that brings me to the end of this presentation. I will be happy to take any of your questions.
Okay, so thank you very much for that presentation. And it looks like we already have some questions coming in. So just a reminder to everybody in the audience to click on the Ask a Question at the bottom of your screen. And it looks like we've already got several questions already. So our first question is, can you measure CO at several locations after the EAF outlet?
We have, so we can, system do not have to be different. You could, for example, mounted in several locations of measurement. That would help to monitor your post-combustion process. Stream of your CO has converted into thermal energy your preheating of scrap, for example, or you can at least calculate the CO is gone.
Okay, and we've got the question, how long does the installation of this device take?
Usually, when you have an installation, you have several steps that you need to do. For example, pulling the cables, setting up the cabinets. This is usually done in the typical time that you need for this, let's say a week or so. The actual commissioning of the system should take 1 or 2 days. So it's not a very long time that you will need to get the system going. And then, of course, maybe at a later point in time, you can do some comparative measurements. But usually a week outage or 1.5 week outage should be enough to get it all done. What you have to take into consideration, though, is the modification of your off-gas duct. You need to put the water box in. So usually people take a longer outage to install this water box. But the measurement itself can then be installed fairly quickly.
Thank you. Just another question coming through. What do you have to control exactly to save energy on the furnace?
Well, I can only talk to them about the manual controls. The manual controls will be really the question, for example, how long you are decarbonizing your steel. So how long do you have your O2 lens going? Lens, when can you switch off the end of the power on? Monitor gas side, optimize the consumption. Scrap people that have optimized or parameters their electrode control furnace in all. I don't, but we know from savings can be around in kilowatt hours, a gigantic amount. So
Okay, I was just reading the next question. So what's the normal lifetime of a sensor?
Well, in a steel plant, that's a good question. We don't see that the sensor wears out by itself much. So we think that the sensor can run for many years. It's not something that it's not a consumable item. What we would recommend 6 months or 1 year. The sensors are looked at. So when you have an overhaul, you have a look at the sensor, and maybe you want to maintain it, clean it. We also offer a subscription model where people can rotate their sensors with us, so they always get a fresh one, a new one every year. Wear out or you know, the lifetime of a sensor should be 5-10 years. Now, of course, sometimes you have a piece of scrap falling on the sensor. You have, splash of steel or slag location, and also keep the sensor protected in order to avoid these things. So some of the installations we've had some damages. In other installations, we've never seen any lifetime wise from a sensor.
Okay, it looks as though that's all our questions for today. So thank you very much. And just a reminder to the audience, once again, that you can still send any questions whilst watching on demand. And all the unanswered questions and future questions sent will be answered at a later date. I would like to thank Hans Conrads for this presentation and Promecon for sponsoring this webinar. And to the attendees, you will receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.arena-international.com. And we look forward to sharing further webinars with you. So please do keep an eye out on the website just mentioned. Thank you once again for attending, and we will see you next time. Thank you.